The moment you try to do anything somewhat complex with it, yeah.
We had a few contacts.
And another thing is, the best thing to do is instead of running it in a debugger, or running it in the emulator, phone up to it. You can watch all the debugging information, you scroll across your live tone,
Delete.
and it's like, oh,
I don't even
it's
know
too
how
bad.
that's on version.
Because it's like, it's
He has two? That's right, he got two.
How is it? Is it as good as
and then
XP?
not only that, I
It's
know
an
that
embedded
it
operating
has
system.
nice
I can't remember, but you know what? It boots up instantly.
Probably don't want to build it.
Does it really? Yeah.
Okay.
Just hit the power
You
button.
probably want to build
Is it full 32-bit? I don't know.
with
It's running on mixed setup.
CE, I think CE might
ICS in mind, but with the minimum
It's a mid
SDK
system?
level
Yeah.
of, I think it's 8,
Like you're writing
which
for
is
software
Froyo.
for it?
Yeah.
No, because I'm pretty.
Because
you can't write
Froyo's
for
on
so
majority of files.
Right.
Okay.
So you want to make sure that it
You can't compile onto the mix.
That's the whole-
like, there's no like,
Yeah.
like the only
and they ask for it. Fragmentation.
you can download Linux for it, but you can strip down.
It's true though, you
Yeah,
gotta.
it's not as good support. That everyone's willing to go Linux like tiny and rare.
No one knows what
It's like I spent like a day trying to do BI on
Because people remember it.
Otherwise, I'd just be a BI.
This is
looks
They
so
actually
much
do
like
have
this.
numbers. It's API
I'm
level
pretty
8.
sure it's
Yeah.
probably 3.1 came out.
Well, that makes, I mean, here you talk about Froyo versus SB7.
The thing is,
They
they've
know it's
updated,
better or worse.
they've updated, like, since they came out,
No,
like,
yeah,
that was, what,
yeah.
a year ago they came out? They're up to, like, API level, what, 13 or 14?
They're 15.
15?
I have API level.
That is a long, that's like double.
Double what it was.
Yeah,
What is it?
so it's
You
not
just
like
came with-
iOS
you know, like
where
how
it's
much
like
is that?
once a year. You didn't-
Yeah,
It's
you're
like-
probably
it's
like
not-
my
Yeah.
Here we are.
I actually still have one.
So,
Yeah.
there's a lot of
I
reasons.
think
that's
I'm-
not true.
Yeah.
Because the
Are you
API,
on the same
I did once.
anyway.
And it crashed.
I appreciate the tips though. That'll make it a lot easier for me to download line instead of being.
Yeah, if you have, like, literally, all you're doing for the camera is spawning an event.
Yeah.
You're going in and you're
Where did you
saying,
get that thing?
I forget how it goes because I haven't had to do it in a while.
But
But it's basically like
read now. What I'm doing is
you using. Oh, another thing you have to know is you have to ask for permission in your Android
Yeah.
manifest
Well, I was,
to use the.
I was,
So keep that in mind.
using one of those, but there's something wrong with it. I don't know.
Yeah, this one was perfectly fine. Like the only
Yeah, but that's a skin.
So it's good. But
That's not stock
Is
in.
that-
That's like your catalog.
yeah.
Pretty much. No, I know.
I'll just need $1 cut off.
The camera application,
It's $6.
the real camera
It's like
application
it's mine. Like that's
is the one that
Hey,
you
David,
see.
you ever
Yeah.
make fluid dynamics?
So,
No, I do not. That's a pain. That's if you do take it. Just
You
mine.
did take it or you didn't?
I didn't take it, but it's a pain from what I've heard from different players. Because you're doing depth div, and fluid.
I love all those. Curl, divergence.
Yeah, so I thought I'm not knowing that you have to use it.
You could use
Use this word problem. That's something the problem. That's you the word.
I was just thinking about that because there's like this little particulate matter in the bottom of my tongue.
Do you have?
You swirl it. At first, it was kind of just like suspended there, but then I noticed it was moving a little bit as the vibration or whatever. It's like,
Yeah.
you shake it around. It's kind of easy.
It's something like that. It's basically it keeps it.
That is really good stuff.
you can do it in software, but it's not nearly as good.
Quantum mechanics.
And then,
But yeah, there's no get to talk about all the different quantum mechanics. It's like,
did you know that they were here today?
no, I did not. Now I do.
Yeah, I decided.
The amazing people are here. That's, hey, Dr. Plants. Here, look, you have David and Zach together.
Oh, hi.
Oh, and Braden.
So if I put my talk on website, I'll bring my laptop too, just in
The clock, of course, is just lazy here in this campus.
All your errata
In the fall, they adjust it and wait for the spring to show up. But anyways, it's noon. noon:45 is when we have to quit. And in case you are going slow, I'm going to be pointing to my freckles.
Okay.
Maybe back 1 second.
And so we should really
Oh, God, don't go.
Are we going to do anything with FLT today? With Fermat's little theorem? Okay, all right. Because,
Nor did the street law. Nor the street law.
okay, good, because that's what David and I have been looking at. We're like, we should spend some more time with this. Are we going to talk more about that today, or are we done with that?
Maybe Tuesday, I don't know. For some reason today I'm very excited. If you're ready. I'm ready. Okay. Everybody do the wave. Hey. We need to get started. So, next Thursday is Ken Loudon's turn to visit us. He is a retired professor of computer science at San Jose State, author of a book on programming languages and compilers, and he will tell us why some languages are more dangerous than others. Today I have the pleasure of introducing you Professor Mike Doherty from the University of Pacific, who will tell us why we soon won't need any human actors. Let's welcome the speaker.
Actually, that's a pretty good introduction of what I'm looking at here. What I'm really going to talk about today is kind of a persistent problem that I've been running into for many years in some of the work we do at the Pacific, and the attempts we're making to finally tackle this problem and finally get to work on it. So I don't really have any great new research results right now because it's pretty much a program that we're just starting up and we're trying to get to see where we can go with it. Anyways, this is me. I'm Mike Doherty. If you want to talk to me about anything later, that's how you can contact me by email. You can find me pretty easy on the web. So this is our basic objective. We're talking about the idea of autonomous virtual characters. And what do I mean by that? I assume you know what I mean by a virtual character. It's a character in a video game, in a movie, in a virtual reality simulation, some computer-generated character that moves around and does things and works. I use the term directable as a way of describing kind of the focus of what we're trying to deal with here. In the sense of, he mentioned, human actors are directable, right? You can tell them what to do and they go off and they start doing it. We would like to have characters in virtual characters that are somehow directable. And what that means is they don't necessarily have to be intelligent enough to develop their own goals, right? That's almost another level of problem. That's a big AI problem that we don't want to really jump into here. But if you define the goals and you tell them what to do, that they somehow are capable of at least generating the motion to do that, right? For instance, if I said, go over there and pick up the telephone on the wall, then maybe you can at least get the character to get over there, figure out how to walk over there, and make all the motions that are necessary to do that. And autonomous, meaning that you don't have to have a lot of interaction with the character to allow it to do it. It can understand the environment, it can move around, and it can do things. And then the third aspect of this that would make it a virtual character, a virtual human character, is to do it in a human way, right? It's one thing to make something get over there and physically pick up the phone. It's another thing to make it do it in a way that actually looks like a human being. And that's what makes the problem a little bit more hard. So I'll just skip that. So the context of this and why am I looking at this problem and why are we looking at this problem is we've run into this same problem over and over again in various things. I teach some courses in game development. I've got a colleague who does virtual reality. I work with a film studies group every once in a while when they have somebody that's interested in animation. And in every place we run into this wall of everything looks great until we get to the people, right? Then we got these either stiff characters that don't move around, we got characters that don't look human. And so how can we rapidly get characters up to speed that start to do things? And then the second bullet here is kind of my background and perspective. I come from a simulation background, right? That's how I think about things. I tend to think about things in terms of simulation, which means I want to understand the system, develop models of the system, and then construct simulations of things, which kind of it has some influence on the way I'm approaching this particular problem. Okay, so problem formulation. I keep coming back to this picture. This is from 2000. It was published in CACM. When I first started working at Pacific, I had a bunch of students wanted to do some game development stuff, so I said, great, we'll have a special topics course, we'll start building games. And we started with this picture, which I'll draw it a little bit better in a second, because I know it's a little hard to see what's going on here. But this guy was talking about, how do we make virtual fish, right? So fish that swim around in a tank, they don't run into things. Pretty simple. But it's got some interesting things. Let's just move to the next slide. And this is the same picture drawn in a way that's a little bit easier to see. So we've got a world database. So this would be your simulation. This is what's out there in the world, all the things that you don't want to run into, all the food you want to eat, all of that kind of stuff is out there in this simulation. And then up here we've got essentially, the fish is perceiving things. It's got some goals that it's making, and it's got some behaviors that it's generating. From that we go to motion generation. Then we go over to appearance, and we start interacting, closing the loop, so we've got something that's actually a running simulation of fish. Pretty simple. How does that scale up to human beings? Well, there's some problems, right? Human beings are a lot more complicated than fish. But if we start going through this picture, this is, not a solved problem. I mean, there's always work to be done in graphics, but we know how to draw stuff. We're really, really good at this. If I go to the faculty at my school, I got at least 5 faculty members and 20 or 30 students who are really good at graphics. We can do this part of the problem. It's not too bad. Down here, if we call that virtual reality, for lack of a better word, again, not a solved problem. There's still a lot of work to be done here, but we know what we're doing here. We've got people that understand virtual reality or game technologies and all the different things, different areas where you might be putting these kind of things together. And then up here, this whole area, what is this? This is really the artificial intelligence of the character. And again, agent-based intelligence, I got a faculty member we just hired who's great in this area, right? So we understand what's going on here. And so that leaves this little bullet up here. And this is where we're always getting stuck. How do we actually generate the motion? If we know what we want to do, we know the environment we're working in, how do we actually generate motion that looks human? So that's really what I'm focusing on at the current moment. Okay. Along the way, since we started looking at that a while back, I read this book, I don't know if you know it, by Jeff Hawkins on intelligence. A really terrific book. And it was just my first experience of trying to start to think of the human nervous system as something that could be simulated, right? As something that does have some kind of structure to it. It does have some kinds of way of dealing with things. And so I started thinking about, okay, maybe this is a solution. Maybe we go in, we've got these high-level goals, we'll let the AI people take care of deciding what we want to do. Can we then turn this into something that we can start sending signals down and generating motion? Unfortunately, that sidetracked me totally with what I call my naive solution, which was to blow the whole problem off to somebody else. Right? We'd say, here's the world. We throw in some big, complicated neural network in the middle, and it drives our skeletons, and we're done. Well, obviously, that's not a very good solution, right? It avoids all the real issues that are in here. And so, in reality, what I'm coming back to is putting something realistic into this block. What can we do that will actually make this whole thing work? Okay. Real quickly, what are we talking about in the end? we're driving skeletons, right? If you know much about computer animation, you're driving a skeleton, you're setting joint angles, and you're pushing bones around, and then you draw fancy pictures and skin around it to make it look better. So we got all kinds of joints. This is a picture of the skeleton that we're currently working with. The reason we're using this is, oops, that would be good. The reason we're working on that is it's based on the mocap data that Carnegie Mellon supplies. They got a nice, huge database of motion capture stuff out there that we can pull in and work with. So what does it mean? It means we got 30 bones connected by 30 joints. Obviously, if you're going to be dealing with hands and fingers and toes and stuff, you'd have to add more joints. But that's what we're working from, and that means that this is essentially what our problem is. Oops. We've got 30 joints. Some of them have 2 or 3 degrees of freedom. We've got 63 degrees of freedom. What does that mean? It means the end goal is I need 62 angles. That's it. You give me 62 angles, I can draw a pose for a skeleton, and I can have some nice graphics. So the question then boils down to how do we generate those 62 angles in a way that makes sense and that actually gives us some kind of motion that looks somewhat human. All right. Work in this area, as far as I can tell, started around 95. This is a picture I just love out of a picture in SIGGRAPH by Witkin and Popovic in a paper they called Motion Warping. And this is a picture of what do these angles look like if you just drew them all down, right? You got 62 squiggly lines, and you're supposed to make some sense out of that to get some motion to drive your characters. And the reason I like this picture is, one, is they just kind of throw it in the paper and say, this is what curves look like. Great, but what do we do with them? But I also like, because when I first started approaching this problem, this is what my brain looked like. It's like, how do I make sense out of all this data? It's just all these big waves and signals and stuff. So that's where we're at. Okay, so what I'm going to go through now very quickly is just some of the different areas of research that we're drawing on to try to come up with a solution to our basic problem here. Again, and well, this is actually from the same CACM in 2000 as the Fitch picture I had there. This is Zoran Popovic, the same guy as the previous paper. If you do any reading in computer animation, you'll know his name. He's quite famous. It would seem that creating realistic character animation would not be significantly more difficult than computing the motion of cloth or other such passive objects. It would seem to be, right? It's just another simulation. But then in the same paper he says this, create the motion of synthetic humans, arguably the greatest challenge in computer animation. So realistically, he's being a little bit sarcastic up here. This is the real issue. I mean, it's really, really hard. And why is it hard? Because we recognize humans, right? We recognize things that are humans. If cloth is a little bit off, it's fine, but it doesn't have any real behavior, it doesn't have any real thinking, it doesn't have anything that we recognize as any kind of human style. So where are we at in graphics? The first few slides here are just going to talk about, if you go into the graphics world, what are people doing and what works. First thing, obviously, we can do really good animations of humans, right? Anybody who's been to the movie theater recently, seen a Pixar movie, we know we can do this stuff. We can do really good animations. Look at some of the video games out now. We can have some pretty good animations in there. So what do? We either have an artist sit down and draw stuff or work with all these angles or produce these angles for us, or we get some fancy camera equipment and we generate mocap data. And so we have all these angles because somebody's actually done the work, right? Very, very intensive in time and labor to do this, but it works. But the real problem is it only fits one scenario, right? And we need to be able to apply this in multiple different scenarios, new scenarios here and there. Next level of work is like the Popovic paper I just referred to, warping, blending, splicing, retargeting. These are all different ways that they've come up with for taking one motion capture sequence and playing with it, or taking a couple of them and putting them together, or modifying them to fit into new situations. This gets really good results for limited behaviors. For example, there's a lot of good work in the video game business for first-person shooter soldiers in a first-person shooter game. They work really well. Why? Because they don't have a lot of behaviors, right? They got 3 or 4 behaviors. You modify the data to make those behaviors work, and they work really well. But they're not going to get up and pour a cup of coffee, right? They're not going to get up and do anything unique that they're not already programmed to do. And this is where a lot of the recent work in graphics animation has been. And then there's physical interaction, which is, okay, now we'll take those characters and we'll make them bounce when you hit them with a basketball, right? We'll make them fall over when you shoot them, all these kind of things, and have a little bit of physical interaction. This is pretty well understood. We're approaching feasibility and runtime with this. The more point, all this stuff is making its way into commercial products. That's always a good point to stop and say, we've done the research, right? The computer scientists have done their job. They've done a lot of really good research. It's starting to become commercialized. Maybe we can consider this a fairly well-solved problem. Not that there's not a lot of work to be done here, but that's not really what we want to be dealing with in our work. I'm going to skip this. This is just talking about the idea of how do we warp things. You know, we take up one pose, we modify it in various different ways, we run a lot of algorithms on it, and we get new walking behaviors out of the original walking behavior. We can do that. Then there's another aspect which would be procedural motion generation, things like inverse kinematics, like figuring out, okay, my hand needs to be here, how do I find all the joint angles that I need to get there? Really just a mathematical problem. It's pretty easy to do. Kinetics would be putting realistic physics on these things. Again, this is pretty easy to do, and I've seen some stuff that's actually surprisingly lifelike just from running physical simulations. They look fairly human, and they work pretty good. But the problem is that this stuff, it's very hard to get any human kind of style on it, right? It's just mathematical equations, and the physics works, and it all works. Physics is great when I'm bouncing a ball or throwing a bullet through the air or anything like that because it's well behaved. But when you have anything that's human, you still got problems. So we need some kind of aspect of style. This is what I was talking about. This is some really nice work out of Riverside. It's a few years old, but basically they're taking some mocap data and then they're applying forces to these characters, and they manage to rebalance themselves, and they do it in actually fairly human ways, just based on algorithms. So we're moving there. We're getting somewhere with this kind of work. That's the smart architecture. I'll skip that. But this, to me, is then where it becomes a real issue, is the idea of style. I like this picture. It's actually just from a poster abstract, but it's a nice picture because if you look at this, just these skeletons here, and you look at the labels, you can see it, right? You can see the difference between sad or drunk or afraid or whatever they've got here. You can see that, and that's the kind of stuff that makes humans human, right? As opposed to something that's a robot or very, mechanical looking. So where do we get style? I'll skip over this in the interest of time. Style is often dealt with in terms of difference, and this actually works surprisingly well. For instance, we can take the analogy. Walking is to running, as strutting is to what? Well, what is it? Well, if we turn the equation around, we can say whatever that is, if we subtract the walking part from the strutting and then add running back in on top of it, we get kind of a strutting run, whatever that would be. And you'd be surprised how well this actually works. Because what we're essentially doing is we're taking out the really high frequency control signals out of the motion and then separating that from the low frequency control systems, which would be like just walking mechanically, and then we're just putting them back on top of the new low frequency things to get the same kind of style. And this kind of stuff works really well. All right, so in summary, graphics and animation. There are lots of techniques, algorithm and math, and they work really well. The problem is application of this stuff can still be very labor intensive. Right? It's not very well automated, and it's often very domain specific. And my argument is that this because graphics is still about rendering. You go into the graphics world, what do? They're trying to draw the pictures. Right? They're trying to take the data and get the pictures. It's not about simulation and it's not about behavior, which is kind of where it comes back to my particular interest in this stuff. All right, so then we have to take a big aside. I just actually got back from a sabbatical. I spent a lot of time studying completely out of my domain. Right? I'm over in this new domain here of neurology and kinesiology. Spent a lot of time with this particular book, The Organization of Action by Gallistel. Trying to understand, if you're going to simulate something, understand the system first, right? So go out and look in the real world and try to understand these systems, and then come back and try and figure out, okay, how can we build some kind of virtual system that simulates this kind of stuff? So we got neurology, which studies the neural system, kinesiology that studies the muscles and the mechanics of animation that we're dealing with here. This is a picture out of the Gallistel book, pretty early in the book. What this picture is really showing is people have been interested in this problem for a very long time, right? This is, I'm calling 19th century motion capture, right? They're hooking up frogs and other animals to different devices and measuring their motion, measuring how they move. trying to get some mathematical description of how do their limbs move and how do their neural systems actually produce those motions. Nowadays, luckily, we don't have to do that to people. We would just put a camera in front of them and scope it out that way. But the point being that there's a lot to be learned outside of computer science, right? There's a lot of things that's already been done that we can work from here. One of the biggest things I'm taking away from this work is the idea of hierarchical command structures, right? If you look at your neural system, and this is where I started, I mentioned the Hawken book earlier. If you look at your neural system, it's not just a signal from the brain to the muscle, right? There's more complexity in there. There's more structure in there, and that's where all the real behavior comes in dealing with things. But what these biology-oriented people are telling us is there's a couple of fairly simple things at the bottom, right? You've got reflexes, you've got oscillators, and you've got servo mechanisms. Oscillators are things that go back and forth. Reflexes are things that react to things. And servo mechanisms are things that try to minimize the distance, right? I want to get my hand here, so it would be generating a signal to get me over there. And so I'm going to have to be very short on some of this, but there's a lot of interesting things here. We've got to find some way then of getting from these really high-level behavioral commands that are coming out of the brain down to the muscle commands that are actually driving our skeletons. And this is just the kind of a picture, a very simple picture of it. But as we'll see once we get to the ends, right now this is really my focus, right? My focus is how do we replicate this? How do we come up with a simulation that essentially does this kind of stuff? And what's interesting here is it not only does it drive the things at the bottom, but in the hierarchy it takes care of problems like conflicting behaviors, right? We've got multiple commands coming from our brains sometimes, and we have to decide which ones can we do, which ones can't we do. We have to be able to turn some things off to override them with other things in order to get things to happen. Simple example, I'm walking along, I'm talking on my telephone, and I trip over a rock. What better happened? Well, all my control that turns on balance and worries about just standing up instead of falling down, better take control over the telephone conversation. Right? Those are the kind of things that we can deal with in this kind of a structure. Similar thing, this is what he's showing here is that the same signals can actually do different behaviors sometimes, right? He's basically showing the same signals are causing this dog to scratch or this dog to lift his foot because he stepped on a nail. Same signals, so how you distinguish between the different signals or the same signals to the same muscles that actually have different meaning. And meaning is obviously a big problem in this as well. And then we come up to this idea of plasticity. This is the way these people talk about learning new muscular behaviors. And to me, that's where it really kind of gets interesting, right? Like I said, the animation people, they're really good at generating one behavior, and it looks good, and it's really great, and it's well-tuned to do exactly what it is. But if we want these characters to learn how to do new things, they've got to have some kind of plasticity, which really means going into these structures and tuning things, right? As you learn new things, what happens? Your body basically just tunes all its parameters in a way in the neural system in order to keep doing the things that work well and to stop doing the things that don't work well. There's one way to look at it. All right. Now, in the interest of time, I'm going to skip over all this. One reason I'm interested in this is my background is electrical engineering and control theory, and so a lot of dealing with sine waves and signals, and what the neurologists and stuff have shown is basically all of this stuff can be broken down into 3 or 4 overlapping sine waves, and you get pretty good behavior. Obviously, if you need a lot of high-level, high-frequency style on top of that, you need to deal with it as well. So we're also looking at how can we break these motion commands or motion signals down into basic signals as well. But in the end, then, what do you got? You got joints and muscles, so you're generating these signals out of here, and you're pulling on these little muscles, and things move around, and you're generating angles, right? And then suddenly you've got some motion. How do you control all that? Well, that's really the hard problem. Okay. Similar things about feedback loops. The other area that we have to turn to for help with this is once we understand the system, we've got to start simulating it. So we can go look at outside of graphics, look at simulation, control theory, robotics, and some other areas here and see what help these guys all give us. because if we go back to the frog, the difference between what they were doing there and what we have now to work with, which is basically motion capture data, is we have the end answer, right? We have the end answer. I need to be here, I need to be here, I need to be here, but I don't have the signals that drove that in the first place, right? I don't have so I don't really have anything I can modify. I can warp this and say, okay, make it go a little bit higher, but I can't really drive a new motion based on the motion capture data itself. So in a way, what we're coming down to is trying to come up with the inverse function here, right? If motion is a function of these signals that the frog or the human's neural system is putting out, can I rederive the signals out of the motion in order to have something that I can work with and play with? And there has been a lot of work done in things like this. This actually was a graphics paper, fairly old, of basically, jump ahead, pushing roaches around. So roaches can walk. Not too hard, pretty simple sine waves, and you can make roaches walk around. Again, does this scale up to human beings? No, for walking, probably. For just getting human beings to walk, probably. To getting them to walk with style, to get them to walk while they're doing other things, we've still got a little bit more of a problem there. I really like the title of this paper, A Robot That Walks, Emergent Behavior from a Carefully Evolved Network, right? So we can do this stuff with networks. We can build these kind of things that make robots walk or make virtual characters, which would actually be a simpler problem than a robot, walk. But again, we've got this carefully evolved. What does that mean? A lot of human labor, right? A lot of human work in here. Instead of doing artwork or mocap work, we're doing human tuning of these networks to get them to work. And that's fine, because it gets us started. But if we really want characters that can do new things and do novel things that they haven't been predefined to do, we've got to have a system that can actually find ways to build this stuff on the fly. All right. This paper, and we actually just spent the last weeks on this paper in my class back at Pacific. This was some early work in trying to build a general reconfigurable control system for human beings. Basically, all this guy does in the end is walk around without running into lampposts. It's not really that complicated, but it's a good start. It's a good start. We've got perceptions over here. We're getting information in. We can reconfigure this network of control nodes inside, and then send that over to a system that actually generates footsteps. So it's a good start. The problem with this is it's very one-dimensional, right? And as I mentioned before, we need a hierarchy. We need something that's a configurable hierarchy of signals so that we can deal with some of the more complex behaviors that we're actually going to be looking for. Other work that's a little more recent, this is Marcelo Kallman, who's up in UC Merced now. He's kind of doing similar stuff in a hierarchy kind of way. So basically he's building, little, how would I describe these? He's building mixers, essentially. They're like mixing boards that you might have in music or something for taking various signals, various motion capture signals, and mixing them together to get the correct kind of behaviors. He's not to the point yet that this is really a reconfigurable thing, but at least it's a really good demonstration that this kind of thing that we're looking for has some potential. Other work, comes from in the robotics world. They've done a lot of work with neural networks to drive things. So driving robots, moving their hands around with neural networks, that all works pretty well. So we might be able to draw on that a little bit for what we need. And then if we jump over to the artificial intelligence world, we've got a lot of stuff we can draw on from there as well in order to get these things to start working a little bit better. I'm going to skip this slide and go to this slide, which is a little more interesting. I actually like this slide because I read this paper just in time. I was starting to put together a big experiment where we were going to try to do this, and then I saw this paper and said, "Oh, we don't need to do this. They've already done it for us." So that was a good time saver. We'd gotten to the point where we'd actually built the hand, and we were going to start putting neural networks in to make it work, and then we found this particular research. So always do your research before you do your work. That's a good lesson to learn there. But what they were doing here is they have a three-fingered hand, and it's got to pick things up in a virtual world, and showing with layers of neural networks that can first learn how to do something, then learn how to do it better. So one network is essentially kind of filtering out and making decisions about what's learned by the other network, that we can make a lot of progress in things that kind of get emergent behavior or new behaviors. There's another problem, and this is the biggest problem that I see for what we're trying to do, which is classification problem. If you know much about AI, there's the idea of classification, taking some big data set and drawing out conclusions about what's in there, kind of related to things like data mining and that kind of similar kinds of work. So we've got this, imagine this big pile of motion capture data that we got that tells us a lot. It's a lot of examples of how humans do things. What can we learn from that data? How can we go in there and figure out what we can do with it? Well, we're going to need some kind of system. Either we pay somebody to sit there and go through each one and mark them up and label them and annotate them really well and figure it out for us, or we're going to need some kind of system that can automate this kind of work. And that would be really helpful. So that's where we're at. So that's all the background stuff we're pulling into this. So what are we going to try to do with it? So we're just, like I said, we're just starting up this project. We're 4 weeks in now, actually. I just got some students starting to look into this, and we're trying to figure out what are we going to do about solving this problem up here of motion generation. We'll assume that these all work, and eventually what we're hoping to do is pull this together with some of the other faculty. And like I said, Dan Clyburn we have who works in this area. We've got Emma Bowring who works in this area. We've got plenty of people to do the graphics, and we can hopefully start pulling this into a bigger working project that will start solving some real problems. Well, the question is, at this point, where are we on this, and are we going to be able to solve it? So, is this a solvable problem? Right? That's my first question. Before we go spending a lot of effort trying to work on this, is this a solvable problem? We got behavioral commands coming in. We need motor commands coming out. We got a little bit of other information coming from physical interaction that we need to deal with. Is it solvable? Well, from a theoretical perspective of computability or something, sure. I'm sure it's solvable, right? Human beings do it all the time. I mean, this kind of stuff can be done. So to me, the real question isn't, is it solvable? Is it a feasible engineering problem, right? I'm taking a more of an engineering look at this and saying, rather than what's all the theory behind this, if we take all the stuff we've already got, all this kinds of information and prior work that we've got, are we to the point nowadays we could start to build these kind of things and make them work? Or are we still a ways away from this kind of thing? My answer, I think so. I think we can. I think we start building these things, and that's what we're actually attempting to do right now. So we're actually now, my students and I are working on just trying to come up with a basic architecture for what's this going to look like as we start trying to build things. And so let me walk you through what our thinking is. So we start out with a database up here, right? Like I said, Carnegie Mellon's already got online a huge 4 gigabytes or something of motion capture data. Really a valuable resource. We can go and we can find all kinds of things about what does it look like to mop the floor? What does it look like to swing a baseball bat? What does it look like to run or walk or dance? So there's tons of motion out there. But how do you go and figure out what this motion is and what you're going to do with it? And that's what I said. This, to me, is the scariest part of the problem. Partly because I'm not an AI guy, and AI scares me to death sometimes. It seems like a really hard problem, but I'm assuming that we've got some ability to deal with this. I think the real problem is a representation problem. We don't really understand yet how to represent the motion and what it means and what are we looking at. Do we want to be looking at the end motions? Do we want to be looking at the trajectories of the motions? Do we want to be looking at the signals that control the motions? That's the kind of problem we're trying to come up with there. But if we assume we can do that, we can start classifying this motion so we know what we're doing. Then as behavioral goals are coming in from the AI system, which again I'm putting outside the scope of my particular work, we've got some kind of signals coming in telling us what we're trying to do. We go and we select these motions as examples, essentially. And we send those down, we break those down into configuration and motion requests into this network of control systems, basically the neural system of our virtual character. And out from that will come motor commands that go down to the kinetics and the kinematics and stuff that we can already do really well. This stuff is pretty easy to do at this point. I don't want to say easy, it takes a lot of work to do it, but it works. We've got this stuff working. We've got systems that you give us the right motor commands, we can generate poses, we can get them to interact with the world, and that's all fine. But there's a big missing piece here, as you'll see, and this is what we're kind of just starting to struggle with. I had this thing here of learned motion, right? So we got motion examples, right? We've got all kinds of examples of things. But real human beings, what do? We learn to do new things. right? How do we learn to do new things? Usually we watch other people do things, or we just come up with new ways to do it, and we learn new things, and then we've got to remember those things, right? So we've got this whole issue of learned motion, which is kind of not connected here. So we're starting to think of the idea of some kind of critic, which is another concept that comes from the AI people, of something that's evaluating what we're doing and trying to remember what works well, what doesn't work well, how can we pull all these things in there and start dealing with it. We're not really quite sure what's happening here, and it kind of, again, depends on our representation of all of this stuff. But the critic actually, it needs another piece. It needs some evaluation from the higher level AI, right? From the higher level brain. I got to decide, when I tried to pick this thing up, did it work or not? And if it didn't work, don't save it. If it did work, save it, right? That kind of a problem. So this is what we'd be putting in here as the next piece of trying to start getting things working. But I think the next slide is basically, what are we really working on at the moment? It's probably easier just to talk my way through it here. Our current focus is really here. Our current focus is just right here, because if we don't get this working, the rest of it's just not going to happen, right? It's kind of pointless. So we're taking the work of Kalman and some of these other guys, and we're trying to see if we can come up with a system here that will allow us to control things from multiple conflicting control signals and actually be reconfigurable as we learn new things. And then the next step we're starting to look at is this part up here, the motion classifiers up here. I'm still looking for some students with a little more AI experience that can help me up in this area as well. So given all that, I think we've got a good start. I think we've got something that's got some potential to get some interesting results here. Certainly, it has the potential to solve these problems I'm talking about, these problems that we've had all along of how can we get more behavior out of our virtual humans in a way that will allow us to avoid all the manual work that it takes to do it. So I don't know if any of you have ever tried to use a tool like Maya or any of these other 3D modeling things. I don't have the patience. I don't have the patience, and most of my students don't have the time or the patience to sit and do all the detailed work it takes to do this. So if we can go up and get examples of motions that are already there and use those to drive some kind of learning process that drives what's really a simulation of a neural system, I think we can get a lot further with this and get some things that are working. Because it's really frustrating. I've had students build a couple of really nice game demos over the years, right? And it always falls short right here, right? Because they end up there. A good example is a game that's called Goat Catcher. You run around and catch goats, and it's really cool. But the problem was the goats had to be basically jet-driven, right? Because we never got to the point where we could animate their legs and actually have any real behavior from the goats. Got a little bit further on another game where you were basically, it was kind of like tag, except one guy was a ghost and some other things. But you had people running around. And so we stole some motion capture data from Half-Life or something. We got the characters to actually walk around a little bit, but that's all they did, right? And it became very obvious very quickly that these characters only had one basic motion, and or two. They could run, they could walk, or they could stand still. And that was it. We didn't have the ability to generate anything new very quickly. So this is where we're at. This is what we're really trying to do, and that's my presentation. So any questions?
Are you doing any work with 3D motion capture? With the advent of newer three-dimensional cameras that can actually capture geometries as opposed to just flat pictures?
No. I have some students that are talking about doing some work with the Kinect system to kind of get that. If you know what happens with a Kinect, it's basically a 2D image, again, like you're saying. So you have to somehow extrapolate the third dimension out of that. So actually what they were talking about is something kind of similar to this, is if we can go find example motions in 3D and then map that third dimension out of that onto the character's motion from the Kinect, we might be able to get the 3D that way. We haven't really considered the 3D camera set. Mostly because that's not really the part of the problem we're interested in, right? We're kind of assuming that somebody else can give us motion, right? I'm not really focusing on how to generate the motion examples so much as if we have the motion examples, we could deal with it in the second case. Which is something I didn't mention, but if you look forward into this world, what's something else that's going to be happening up here, right? What's happening with almost all aspects of computing, right? The big data issue, right? We're just collecting so much data about everything all over the place. Same thing's happening here. People are doing all kinds of motion capture data. They start putting it on the web. We have all kinds of, as we get better at extracting motion from flat pictures and flat movies, suddenly we can start generating tons and tons and tons of data, tons of examples, tons of information about how humans actually move. So that's where this stuff becomes even more important, right? So how do we make use of that data as we go forward? I think that's a really interesting driving question for this. Yeah.
To what degree are companies like Boston Dynamics using human virtualization and modern creation of bipedal or quadrupedal robots?
Boston Dynamics, I'm not familiar with. Are they robotics?
Yeah, they make a bipedal robot that walks on its own.
Okay.
So are they like interacting in a virtual world, or are they using sensors, and like how would this virtualization improve the field of robotics?
Yeah, that's a good question, and I buzzed really fast through all my slides on robotics and what's going on over there. I think one part of that question is, what's the difference between this and robotics, right? I mean, what do you think is the difference between building virtual characters in a movie or a video game or virtual reality and real robots? Where do real robots exist, right? In the real world, right? So where do they get their information? Obviously, they got to get them from sensors and things in real time. The other thing so I think what robotics is really good at is, given a specific problem in a specific configuration, make it work, right? A very engineering-directed solution. They can make this stuff work. What makes the stuff that we're looking at different is this idea of it being virtual and being human-looking as it moves around. And I'm sorry, I talked my way out of your question. It's okay to repeat your question.
I was wondering if, like, modern robots are running around in a little virtual world inside their little robot heads, or are you trying to move towards that?
I'm not trying to move towards that. Are people moving towards that? I would say the same thing about human beings, right? Are we moving around in little virtual worlds inside of our heads, or are we moving in the real world? Actually, I could probably point you to some interesting work on that idea. Obviously, the robot has some map of the world in its head, right? Obviously, the robot has to have something up there that's its perception of what the world is. If you want to call that a virtual world, fine. But it's not really a virtual world because it is interacting with the real world. It's its own internal representation of what's in the external world. In my interpretation. Yeah.
As far as generating emotion, have you seen any work on like what mirror neurons do, or if they see an action, they can fire at the same as if they were performing the action?
Wow, I haven't looked at that in a while. Yeah, I think like the Hawking book talks about that kind of stuff a lot. Yeah. Thank you. I need to go back to that because I think that's a word I've been looking for, and I need to go back to those ideas. And I know we're running out of time. But essentially, that's kind of the thing that I'm driving towards, right? Is this idea of take the examples, learn from the examples somehow by replicating the behaviors, and then figuring out what works and what doesn't. Yeah, thanks.
We have a few minutes for more questions.
Oh, we do.
So what if you are presented with 3D captures? What if the data changes? What if instead of getting all this 2D data, suddenly there's a big shift in the kind of data they're providing and they move towards 3D capture? Is this model prepared for that?
This model is assuming that. I mean, I'm not doing anything from 2D data at all. I mean, everything that's coming in is assumed to be 3D data in the first place, right? I mean, motion capture data. Everybody knows what I'm talking about when I say mocap data. I'm throwing that word around like we've all seen all the DVD extras on the Pixar movies of how, you get, or Golem or whatever it is in Lord of the Rings, right? Thank you. Right, we put a bunch of sensors on people and we measure in 3D space where they are, and then we do basically the kinematics to measure all the joints in between, and that's what you get. You get a big pile of joint measurements out of it that tells you all the different poses were. It's all discretized. That's what we're assuming we're working with. That's why I'm saying the other problem of can we take 2D data and turn it into 3D data so that this works, that's another issue. That's kind of outside of here. But there is work being done there. There's actually really good work being done in that, and it's certainly a feasible thing to be doing.
What is your ultimate goal out of all of this?
What is my ultimate goal out of all of this? Like I said, is to have, this is a bit of an overly lofty goal, I admit, right? I mean, and that's kind of a way of driving my students to look at something bigger picture than what we're actually trying to do. My actual goal would be to be able to get some systems in here that can actually take signals coming out of here based on motion examples here and drive the skeleton to do some behaviors that it wasn't pre-programmed to do. Essentially, that would be our structure.
In microscopic world, for example, people are also studying quite extensively about protein folding.
Okay.
And things like that, so virus and things like so. In microscopic world, emotions are also extremely complicated. Is there any way that there could be some analogy or some knowledge from that can be used in the macroscopic world motion?
If I understand what you're talking about, I think that's the kind of stuff that's happening down here, right? And it's kind of bypassing all of this. It's taking the structures of the poses, as I would call them, and working backwards to the signals that drive it, right? So certainly it's an analogous problem. It's certainly the same kind of problem. Work back to find out what are the control signals, what are the physics that generated this particular set of poses or this interaction between poses in the first place. So that's an interesting idea. Something we'll have to work on. Good.
Any more? Well, let's thanks to this speaker.
Yes, you did.
We heard that.
Have you seen the two-legged doing that now? Yeah. You're going
I made the change and it got faster, but it didn't get.
Have you seen Spielberg's Tintin?
Not yet.
That's just in reverse. In other words, they motion captured human beings and made them into cartoon characters.
Yeah, I stumbled across your course instructions for how they have to bring in
Well, it's
summary before the talk. I thought that was an interesting idea.
coercing them to be prepared to understand what they speak.
Right.
In AI, there were always lofty goals. Like, for example, one of the first goals was to create a program that would play chess.
Right.
And it turned out that the way to do it is to have this giant database of millions of chess games and have an effective search technique. But no discovery of any secret algorithm.
Right.
Per se. So it may very well be here that you would have this gigantic database.
That's what I'm thinking. In a way, that's what I'm really thinking. Is, rather than sitting and trying to program up the rules, let the system
Let's go have lunch.
I don't go to lunch.
No, that's probably good. Unfortunately, I didn't warn you that this is a new project. I hope you were able to.
As soon as we walk out, then we'll.
Okay.
5 or 6 students there for the
Okay.
first hour or so.
Okay.
See you later, Robbie.
I heard about 311.
Oh, yeah. I was laughing.
I'm glad. I told you, I thought.
You're right.
Yeah.
You said, wow, it's going to be like that the rest of the semester.
Well, you got everything with the Bible, that's it. So honestly, what do you think after?
Spend 24/7 on it.
I have been. That's the problem. Yeah, more than one. Should I just read these stuff and just read them yesterday? Getting actually caught up on where.
You have to have your old papers, but then it's stapled. What? Crappy stapler. You can't get paper from Jason. Can I get some paper from you? Yeah. Did you go to 496?
What?
Did you go to 494?
Yeah.
For the people?
I wasn't you did that, nobody was. No, he didn't show up.
But it's really nice.
No.
And he wasn't involved in either. Funny. He's a boy. Well, he used to be. I haven't started it. I felt like part of the first one. No, almost all of them. Yeah. But then two, I like.
Just get started in the morning.
I don't really know what I'm. You know, I haven't really looked at this.
So like,
I think it just says like
even
build
if we wanted
but
to,
this one's not
we could even
specific.
put the captions outside.
Devin and Rashad, like they were all with
Yeah.
here.
So,
You have another class after, right?
Yeah, 311.
311 after.
but like,
I don't really
like
have that.
we're gonna let my mom like do all the like
Yeah.
the
that
cutting
was
around like all
right,
the
so another one
fireplace
around
and windows and stuff as far as the cleaning goes. So we can just throw the tape, and then they can just come up and do that. Because that only takes a little bit. And we should have plenty of time.
That has an old thing. Especially because we have testing class. Yeah. A whole week later is kind of a big deal. Finish our work. Yeah, whatever. How are you feeling about that stuff? I understand. It's just translating. It's just math.
Keeping it in your pocket. Consuming it.
Yeah.
But I mean, it's not.
I feel better now.
Yeah. We can go over it. I understand very well.
It's just hard to
Just trying to get ready for the testing.
I was talking about this. I didn't really have time to eat it.
When's your other test? Thursday? Okay. But I just want to.
I'm not coming to office. If I get out of here early, I'm just spare.
And then
I'm just
that like weekend before. Yeah. We can just do a bunch of problems after.
No, I'll go.
Or you say one of us has to say. Thanks,
You took on the team that just saw a lot last semester. I don't know.
One way at least is if I keep him here. So if he sees me,
Yeah.
that's not.
I finished my third return today. Oh, like 50.
Would everybody want?
No. I'm just like, I'm doing my whole thing over the entire internship and just like as a victim of it. No, not 50, 20. And some of them are little. It'll take me a week and a half to do 3. They all 3 suck. Like there's something stupid on all of them. B, they're my first ones. So.
Are they exciting so far?
I can tell. At least one manager is. It's just hard because there's like some of the stuff I don't even know what to ask.
She's getting pretty good at that now.
She's like way around the other side of the office, so like
You can't really
I never really get to see her. You know what I mean?
Is she the same level as you?
They haven't hired anyone in 2 years. They haven't hired any class people in like 3 or 4.
She's probably not going to hire for that.
They hired her, Caitlin, as well as Jen all at the same time, like 3 or 4 years ago.
The premium, that's something for me later on in the year. Later on in the year.
Oh yeah. We're getting some experience hired. Come on down. You fit in so well there.
Well, that's to do.
They just give each other shit all day.
Are you serious?
It's awesome.
It's just like you never leave all day.
And there's like one manager who just like picks on the guys so bad. Like this one guy Ryan, who was glaring with Whitney Houston on his earphones. He didn't have headphones like after hours. And he was like glaring Whitney Houston. And so he just comes up to me and says like, "Oh, what's up, Houston?" And he goes, "Houston, we have a problem." He didn't get it.
Yeah. That's pretty fun.
Like mid-30s probably.
It's kind of like teaching them as you go. But each candidate should giving you prior years until you can figure it out.
Yeah, but they're never the same.
Well, the numbers aren't the same.
Even the activity is not the same.
Really?
Like the second one is dissolving. Like they sold everything last year and they were dissolving this year.
So you're on Google and you're trying to figure it out.
Yeah, I mean we have our like research stuff that's
Oh,
like
they have database for you.
yeah, but even then like, it's hard to know what to search. You know what I mean?
I think that's only like
Yeah.
Even though we had access and everything.
And I'm just now figuring out how to fill out the forms. Because like there's some forms they don't tie to anything on your work papers. So you just have to figure it out. It's annoying.
Well, that's why everybody said it takes about a year and a half for you to accomplish the entire thing.
That was freaking me out last night because I pretty much decided that's what the first 5 years of this job are like. Just when you get a handle on it, they give you a bunch of music.
I think about 2 years, right before you become senior.
But then you become senior and it's all over again.
Yeah, then you get a whole new set of 5 years ago in college, doing nothing.
That's the one thing about this though, you don't really move up very quickly. I mean, they bump up your pay, but no, they don't jump. I mean, Gavin's like sad.
But she gets paid for it, right?
Yeah. No, not first year. I mean, I'm pretty sure they bump your pay every year. But,
So pretty much if you become a partner and the government you're better.
you've been there forever. Like, we're just not growing
I
enough
wonder
to...
what you get like
And nothing new, so it's not like there's a need for anybody
So
to...
there's a low turnover.
There's like
in compared to
pretty much no turnover.
At least it's set up, right?
Yeah. All the friends that I'm getting, there's one girl that left last year that was hired the same time as Gavin and everybody. So I'm getting all of them because she doesn't. Other than that, they're pretty set. Other than
So you feeling
they don't have like super simple nursing, they can make stuff.
I do review session, but like review session didn't really help. You're just getting confused himself.
Like I'm going through and verifying every single plan.
He doesn't write anything out there. I'm not writing it down. You're just scrambling.
Meetings, and they bring golden spoon.
But I may have forgotten to get a green.
Golden spoon. And they just like,
It's late today for a test day.
He's like, you know,
kind of, yeah.
Can we say, I'll let you cheat? Yes, sir. Well, I mean, that's different.
Yeah. It's pretty right. So sad. Looking like you did decent.
Hopefully it goes quick. Thanks. Hopefully it goes quick. Yeah. So I got him started with class. We're not ready to work.
it sucks when you gotta press really hard.
If you have multiple, yeah. Wasn't that bad?
I found out one more sheet of paper just in case.
My super ridiculous is put together.
Yeah, that's 30 seconds. question he totally didn't answer, and I asked about it not Tuesday, is Bruce talks about he talked about like that if there were something but I never said about the party. Yeah. I think the answer is no. It's a whole yeah. The only time you would increase, like the increase in amount of stocks must be related to each other would be through the if effect, which is different than the definition.